Welcome to Physics with the Favorite and the Bad Child, where we will be discussing torque.
Torque, yes. And torque, as you all know, the equation for torque is tau equals force perpendicular times d, which is distance from the fulcrum. Or it could also be force times distance perpendicular to the fulcrum. Or if you have an angle, it could be force d sine theta. And now we will be showing you a practical application or demonstration of the
torque bar.
Yes.
Which determines how much Newton meters of force we have applied when we push down on the bar, which is held by a bolt.
Yes. And that will
be right there.
As you can see, the torque bar is suspended in a parallel position to the ground, so that we don't have to deal with the sine theta problem. And it is turning or applying torque to one of the lug nuts on my car. And this display here will show us how many Newton meters are being applied to a fulcrum by this weight. As you can see, this weight is 25 pounds or 11.3 kilograms. And we will be putting it on different positions, different points on the bar to see how the torque varies depending on the position. So first, we'll put it at 0.6 meters or 2 feet. We have a torque of about 67.5 Newton meters. Now, when we move the barbell closer to the fulcrum, the torque will change. So here, when the barbell is at about 1 foot or 0.3 meters, the torque applied is approximately 33 Newton meters.
And now for the equation part of our demonstration of the torque bar. As we all know, the equation for torque is F parallel to the distance.
Equals tau.
Equals tau. And since we're not dealing with any strange angles, we can disregard FD sine theta.
And one thing to note that's going to be a part of our equation is that F equals ma, as you all know. Just to prove that we didn't need to do the sine theta, here's our torque bar and the weight. As you can see, it's applying a force downward at a 90-degree angle, so then the sine theta is going to be 1, and we can just say this F parallel. Perpendicular, that is, sorry.
Perpendicular.
Perpendicular.
So, our equation, F, which is mg, times d,
0.6.
yes, 0.6, is 9.8 meters a second squared, times 11.3 kilograms, times 0.6 meters. And we get 67.55 Newton meters, which was pretty close to what we got when the weight was at this point on the torque bar.
Yes.
And when we moved the weight further up to at about 0.3 meters.
Or 1 foot.
Or 1 foot, approximately. We plugged it back into our equation, except instead of 0.6 we had 0.3, and we got 33.22 Newton meters, which is about half as much as 67.55.
This shows that the correlation between torque and distance from the fulcrum is a linear relationship, so that if you halve the distance to the fulcrum, the torque will also be halved.
Halved. Now, some real-life applications. If David here is working on a flying rocket. No. What's a missile?
Science class.
Rocket by the USSR, the United Sprague Super Rockets.
Yes.
You see, if David has a small...
United Sprague Super Rockets, I mean, come on, what else could the USSR stand for? Racist, we know what you were thinking.
If David here has a small short wrench,
like this,
it would prove to be very difficult to tighten down this bolt on his rocket. He'd be making this face, because it's difficult. He'd be strained. Now, if David had a much longer wrench,
such as this one,
it would be much simpler for him to tighten down that bolt. See, he's much happier now, because it's not as difficult.
Yes.
Another real-life application would be if David had a nail and a piece of wood, He was trying to pry it up with a small, short hammer. It would prove to be very difficult. And if David applied more force, it still might not work. He would scream things like "scree" and be very distraught and strained because of the extreme amount of force required to take out that little nail. But if he had a crowbar
with a much longer arm, I would have a lot more torque under my belt or in my hands.
Both.
Yes.
This is another demo that we will show now.
Okay, here we are with our board, and a nail, as you can see, is jammed right in the middle of our board.
This pesky nail.
Pesky nail.
Can't have this.
Cannot have that nail.
It's in the way of things.
Alright, and Mitchell here is going to demonstrate. He's going to attempt to remove the nail with a hammer.
With a short handle.
Short little hammer.
Scree.
Scree. Can you hear that? The screeing.
Scree. Very difficult.
Mitchell, take this huge, long crowbar that will help you in assisting you with helping you remove that nail from that there board.
It will sure helping me. Scree.
Oh, would you look at that? And the nail is officially...
That is one nail that is no longer in a board.
No longer in a board.
No longer
Get
in a
it?
board.
Longer, because we're talking about length and moment arm and fulcrum stuff.
Longer.
Torque. No
Yeah.
longer. Yeah. Play tennis.
Hardcore parkour.
Here we are again with the favorite and the bad child.
Favorite and the bad child.
Favorite and the bad child. And first of all, while we're here, I would like to explain to you the reason we have torque bars.
And bolts.
And the reason we have bolts, yes. The reason we have bolts is to fasten things together, such as wheels and cars. Should be separate if they're on the road. Bolts and nuts act as springs. If you tighten a bolt too tight, it will stretch the bolt out, and the bolt will be a lot weaker, and it won't be able to hold the two things, the deal to the other deal, as well. And also, if you don't tighten it hard enough, it will be a lot looser and not as tight, and it would also not be as strong. So
it wouldn't hold the deal to the other deal.
The two deals. Yes. That is why there are torque specs that come with just about everything on a car. Make sure that nothing is too weak of a joint or a strongness. So
Yes.
that is why we torque things to spec.
Indeed. Our last example would be a teeter-totter. You see, I am 160 pounds, and David is 150 pounds. This means that I would stand just a little bit closer to the fulcrum than David would. And by doing so, we would maintain balance, like Taoism, yin and yang.
Yep.
Well,
Yeah. Turns out there was not a teeter-totter here, so we can't really
this
do
is,
our...
yeah. This is where we would do our teeter-totter thing,
Maybe we
if we had a teeter-totter. We're just thinking we've been doing the video thing for like 4 hours now.
Just shout out to Doherty for giving us the idea for
Shout
pretty
out
much
to Doherty.
pretty much our
Doing everything for us.
pretty much our
Telling us
whole
exactly
project
what to do.
would have been nothing without him. Yep.
Yep. If it was for Doherty basically telling us exactly what we should do, we wouldn't have done anything.
At all. Maybe like a little bit of something.
A little bit.
You get those cool shots where it's like, yeah, this is because we're driving in
Drive by
the city.
cities.
What? And as you all know, the equation for torque, the equation for torque is that T and torque. As you all know, the equation for torque is tau equals force parallel times d, which is the distance from the fulcrum. or it could be force times d parallel perpendicular. I said parallel again. Let's start over. I keep saying parallel. Roughly 67.5.
It's all blurry.
Huh?
It's all blurry, like it won't focus. Like
Mitchell, you're not even hitting the board.
no, I'm killing a spider.
Oh. Missile, deal, and
Rockets.
yes, rockets, missiles.
Missiles.
I say missiles.
Who says missiles? We're
Missiles.
not working on any missiles. They don't blow up.
Come on. And the reason we have torque bars is because a bolt acts like a spring. If you tighten it a lot, it will be a lot more stretched out and